Okay, let's jump right into this explainer. Today, we're taking a deep, documentary-style look into one of the most transformative technologies of our lifetime, quantum computing. We're going to journey all the way from the fundamental physics operating at the atomic level right up to the massive global economic impacts we are literally seeing unfold today. Now, I want to hook you right away with this quote from our source material, because honestly, it perfectly captures the defining reality of this year. In 2026, quantum computing stopped being a physics research project. It started becoming a scalable engineering discipline. For years, this whole field was stuck in this sort of almost there phase. Super promising, sure, but practically limited by the immense fragility of the systems. But the milestones hit in 2026, they've moved the field forward in incredibly concrete, measurable ways. We're officially shifting from theory to reality. So, Section 1, the physics foundation. Because before we can understand the billions of dollars flowing into these massive machines, we really need to understand exactly what is happening inside them. The fundamental difference between classical computing and quantum computing is absolutely wild. Your laptop processes data in classical bits, which are deterministic. That means they are always either a 0 or a 1, and crucially, if a bit flips by mistake, classical computers can just copy that information multiple times, check for errors, and basically take a majority vote to fix it. But a quantum computer uses qubits. Thanks to a property called superposition, a qubit can represent 0 and 1 simultaneously, which lets it evaluate multiple complex possibilities all at once. But here is the catch, and it's a big one. Because of a fundamental law in physics called the no-cloning theorem, it is physically impossible to copy an unknown quantum state. You simply cannot copy a qubit to correct errors. And then we add entanglement to the mix. This is a non-local correlation between qubits. Basically, it means the state of one qubit is directly linked to another, enabling parallel processing across incredibly complex state spaces. This right here is the real engine of that exponential computational speedup. But the massive engineering hurdle? Decoherence. Qubits are unbelievably fragile. I mean, any microscopic noise, a tiny fluctuation in heat, or even a stray magnetic field causes the entire system to just crash. Preventing that disruption is the central problem facing quantum engineers today. That brings us to Section 2, the hardware modality race. Right now, zooming out to the actual machines, there is no single universal quantum computer design. We are right in the middle of a massive hardware race. And this brilliantly illustrates the 4 leading hardware approaches, each making critical trade-offs. First, superconducting qubits, championed by IBM and Google. These use tiny circuits cooled to near absolute zero. They're incredibly fast and leverage existing chip manufacturing, but again, they are super fragile. Then you have trapped ions, from companies like IonQ and Quantinuum. These use actual atoms trapped in a vacuum by lasers. They boast exceptionally high quality and coherence time, but they operate a lot slower. Neutral atom approaches from QuEra and atom computing use optical tweezers to arrange atoms in 3D grids. That gives you great connectivity and moderate coherence. And finally, photonic qubits from PsiQuantum and Xanadu use actual particles of light. They operate at the speed of light and can work at room temperature. But making those photons actually interact to perform logic gates, that is a massive engineering hurdle. Now, beyond those 4, there are a few other major contenders. Microsoft is making a high-risk, high-reward bet on topological qubits. They are trying to braid quasi-particles together, kind of like a knot, so that the information is protected by the physical shape itself. If it works, it solves the error problem right at the hardware level. Meanwhile, Intel and Dirac are pushing silicon spin qubits, hoping to leverage the existing trillion-dollar global semiconductor manufacturing industry to eventually just stamp these things out cheaply. And there are even exotic early-stage experiments out there, like EuroQ literally trapping electrons on liquid helium. Yes, you heard that right, liquid helium. The pure creativity here is just astounding. Moving on to Section 3, 2026 error correction breakthroughs. So, with all these unbelievably fragile physical systems, how do we actually compute anything useful? Well, that brings us to the most technically significant milestone of this year. The big shift in 2026 is moving from those fragile physical qubits to stable, error-corrected logical qubits. Researchers have proven they can combine many physical qubits together to act as one highly protected logical qubit. But the real game changer is a technique called lattice surgery. Because remember, you can't just pause a calculation to fix errors. Actually, scratch that. As we talked about, you can't even copy them. So lattice surgery allows engineers to safely split and manipulate these protected logical qubits mid-operation. That is huge. It means we can finally execute continuous calculations without derailing the whole system with constant bit and phase flips. Google also proved the reality of scalable error correction with their Willow chip. They developed a fascinating technique called quantum echoes, which relies on constructive interference. Think of it kind of like noise-canceling headphones, but in reverse. By sending a carefully crafted signal into the system and reversing it, they listen for a quantum echo that actually amplifies the exact signal they want. Because of this breakthrough, researchers demonstrated that as their quantum systems grow larger, the logical error rates actually decrease rather than increase. This is quite literally the exact threshold we needed to cross to make fault-tolerant computing a reality. All right, Section 4, the corporate quantum battleground. Let's zoom out a bit and look at the corporate titans racing to dominate the quantum cloud infrastructure. The big four tech giants have distinctly different battle plans here. IBM remains the frontrunner when it comes to mature, direct hardware access. They're vertically integrated, building their own superconducting chips and pairing them directly with their highly popular Qiskit software on the IBM Quantum Cloud. AWS, on the other hand, takes the complete opposite approach. Amazon Bracket is a hardware-agnostic marketplace. They broker access to many different vendors, letting users experiment to see exactly what works best for them. Google is treating this much more as a deep research play, focusing heavily on a strict roadmap to fault tolerance rather than chasing immediate commercial cloud revenue. And Microsoft, they're playing both sides. They are researching their own highly advanced topological hardware while also offering a hybrid cloud marketplace on Azure. We've seen some truly massive corporate milestones hit recently. Microsoft unveiled their Majorana chip, officially introducing that topological core we mentioned earlier. Atom Computing and Microsoft successfully controlled a staggering 1,225 neutral atom qubits. IBM integrated their quantum primitives seamlessly with classical CPU and GPU nodes, proving that for sure the future is absolutely hybrid. And AWS expanded their partnership with QuEra, committing to launch the Libra system by 2028, which is aiming to execute 1 million quantum operations over hundreds of logical qubits. Section 5. Follow the quantum money. With the technology advancing this rapidly, where's the smart money actually flowing? $36 billion. Let that number sink in for a second. That is the massive collective valuation of the major public pure-play quantum companies today. We're talking names like D-Wave, IonQ, Rigetti, and the newly listed Quantinuum, which went public on the NASDAQ at a roughly $10 billion valuation all on its own. Wall Street is clearly treating these companies as long-dated bets on a technology that could entirely reshape global computing. Now, in the private startup space, overall venture capital actually slowed a bit to $1.2 billion this year. But analysts are describing this as a flight to quality. Investors are ignoring the speculative pitches and pouring huge money into companies with proven, realistic scaling pathways. Just look at these deals from a single month. Photonic Inc. raised $200 million at a $2 billion valuation for quantum networking. QuantWare raised $178 million for a dedicated quantum fab, and Quantum Motion secured $160 million for their silicon transistor approach. The capital is aggressively concentrating on the most promising engineering. Geopolitics are also playing a massive role here, with government initiatives heavily driving the ecosystem. For instance, the U.S. government recently granted $1 billion to IBM to build out a domestic quantum computing chip foundry. That's part of a broader $2 billion initiative through the Commerce Department. Alongside programs from DARPA and the Department of Energy, these national-level investments are actively de-risking the hardware and ensuring these critical supply chains remain strictly domestic. Section 6. The 10-year horizon. So what does this all mean for us? Let's move ahead and see how this builds, looking at realistic adoption timelines and the societal impact over the next 10 to 20 years. Let's walk through this strict, data-driven timeline toward genuine fault-tolerant utility 2026. It was all about proving error correction at scale. By 2028, AWS and QuEra plan to launch the error-corrected Libra system. By 2029, both IBM and Google are targeting the debut of massive fault-tolerant systems, IBM with its Starling processor and Google aiming to control 1 million physical qubits. By 2033 and beyond, we are looking at broad industry adoption where these machines aren't just novelties, they are fully integrated into daily utility-scale enterprise workflows. When that utility scale arrives, certain industries are positioned to benefit first. In pharmaceuticals, quantum computers will run molecular simulations with unprecedented accuracy, literally revolutionizing drug discovery. Aerospace and defense will use it for multiphysics simulations to design vastly superior materials. Finance will see exponential leaps in complex algorithmic optimization. And in energy, it's going to be utilized for sustainable resource modeling and advanced climate tech solutions. The real-world applications are going to be staggering. But as they say, with immense power comes immense responsibility. Take healthcare, for example. The sheer computational power of quantum systems to process vast biological datasets immediately runs into strict patient privacy laws and regulatory compliance. As we develop this tech, we are going to face massive ethical hurdles. We have to ensure equitable access, prevent algorithmic biases, and maintain patient autonomy when machines can simulate your personal biology down to the atomic level. It's a conversation we absolutely have to start having right now. We have moved from theoretical physics to scalable engineering, unlocking the ability to simulate the very building blocks of nature. So I want to leave you with this. If quantum computers can simulate the very building blocks of nature, what industry will remain unchanged in 20 years? Thank you for exploring the quantum frontier with us today. Keep learning, and I'll see you in the next explainer.